This video is going to take a look at part 4 of your gas law unit notes, the combined gas law. The combined gas law is described as P1V1 over T1 equals P2V2 over T2. We're looking at 3 of the 4 variables that can be used to describe a gas, and we're assuming the amount of the gas, our N, is constant, so that's why that one is not included in this gas law equation. We have 1s and 2s as opposed to our ideal gas law because we're looking at the gas under 2 different sets of conditions. At one point it will have a set pressure, volume, and temperature, and then at a second point it will have another pressure, volume, and temperature. And the ratio of the pressure and volume product divided by the temperature should be constant, and that's why we're able to set these two equal to one another. Because fractions are not always the easiest to deal with, we're going to go ahead and rewrite this as a straight line equation by cross multiplying. So that P1 and V1 will go over with T2, and then P2 and V2 will go with T1. This gas law equation does not have a set constant, and because of this, that's why we have the 2 sets of conditions. It also gives us some flexibility with our units for pressure and volume. Our pressure can be in any unit as long as it's consistent between P1 and P2, and the same goes for volume. Temperatures, however, have to be in Kelvin, and that's because you can have negative Celsius temperatures, but you truly can't have a negative volume or a negative pressure. So any gas law we use that involves temperature, we will always have to solve for temperatures in Kelvin before we can use them in our gas law equation. So we're going to look at 3 examples involving a combined gas law. This first one's a little bit different than the other 2, but I want to make sure you're familiar with different ways that this question can be asked. So we're heating a gas from 263 Kelvin to 298 Kelvin. We're also increasing its volume from 24.0 liters to 35.0 liters. And we know what the original pressure was, 1 atmosphere, and we want to know what the final pressure would be. So if we use our combined gas law and we look at what we're being asked to find, we're being asked to find the final pressure, and the final pressure is probably best going to be represented in our equation as P2. So if we were going to isolate P2 by itself, we would keep everything that P2 is equal to on the left side and divide V2 and T1 into those 3 quantities. So P2 would be equal to P1, V1, and T2 multiplied together, divided by V2 and T1. So in our problem, we should have been given information about these 5 quantities, and we should be able to use those to solve for P2. As opposed to going through and looking for each of these individually, we're going to go back and just kind of read through the problem. When there's 2 sets of pressures or volumes or temperatures, it might be a little trickier just to go through and identify them individually. So we're going to see if reading through the question will help us. For example, in this first one, we see we're going from 263 Kelvin to 298 Kelvin. So we started at 263, we went to 298, so there's our T1 and T2. Sorry, didn't mean to hit that. Our volume is increasing from 24 to 35.0 liters. So the first one would be our V1. The second one would be our V2. And then we were given the original pressure was 1.00 atmospheres. So that would be our P1. And I believe that accounts for the 5 quantities we were looking for to solve for P2. So at this point we can just substitute them into our equation. There's the 1 atmosphere for P1, the 24.0 liters for V1, and the 298 Kelvin for T2. We're going to divide those by our V2, 35.0 liters, and our T1, 263 Kelvin. If we use units, if we look at what units will cancel out, we'll see that our liters are gone as well as our Kelvin, leaving us with a unit of pressure, which would be appropriate to solve for pressure N. Again, you've got 2 numbers in the denominator, so please be careful with your calculators in terms of calculating this. We need to multiply the 3 quantities on top and divide by the 2 on the bottom. They all have 3 sig figs, so we want 3 in our answer. And I believe when you do that math, you'll get 0.777 atmospheres. Our second question is giving us the information for the gas at one point together. So we see the volume, the temperature, and pressure are listed together in the first sentence. The gas has a volume of 750 mils at negative 23 degrees Celsius and 250 millimeters of mercury. And we're asked what would the volume be at 227 degrees Celsius and 625 millimeters of mercury of pressure. I always label them the ones I see first to get my ones, and the ones that I'm looking for at the end get my twos if there's nothing that would help me see the difference between initial and final. So I'm going to go ahead and identify this one as my V2. So if I take my combined gas law equation and I recognize that I'm solving for V2, I realize that I need to move P2 and T1 over to the denominator of the left side of the equation. So V2 would be equal to everything that was on the left, P1, V1, and T2, and it would be divided by the two that were next to V2, P2 and T1. If I read across, I would see that the first volume I get to is 750 mils, so I'm going to assign that V1, and everything else that's associated with this volume would be at 0.1 as well. So negative 23 degrees Celsius would be my T1, and 250 millimeters of mercury would be my P1. So that gives me a volume, a temperature, and pressure at one point. I'm solving for the second volume, so anything associated with that second volume would be 2's as well. So this 227 degrees Celsius would be my T2, and the 625 millimeters of mercury would be my P2. At this point, I should be able to substitute into my equation. I think I have all 5 that I'm looking for. But remember what we talked about with temperatures, how they have to be converted to Kelvin before you can use them in a gas law equation. So P1 can go in 250 millimeters of mercury. V1 can go in 750 milliliters. But T2 I'm going to need to find in Kelvin first. And so if I add 273 going from Celsius to Kelvin, I get 500 Kelvin. The decimal place is there because I want to keep the same number of digits either before or after the decimal as in my initial Celsius temperature. I'm then going to divide by P2. Because P1 and P2 have consistent units, I don't have to do anything with that. My T1 is in Celsius, so just like with T2, I'm going to have to take 273 and add it to that T1 temperature of negative 23, and that gives me a Kelvin temperature of 250 Kelvin, which is out to the ones place again because the Celsius temperature was reported to the ones. That allows my Kelvin units to cancel, and that should leave me with milliliters, which would be an appropriate unit for volume. The millimeters of mercury units cancel, as do the kelvins. I multiply the 3 numbers in the numerator together, and then I divide by the 2 in the bottom, again watching out for the calculator issues that are associated with dividing by 2 numbers. My pressure had 2 sig figs. My first pressure had 2 sig figs. My first volume had 2 sig figs. My temperatures both had 3. And my second pressure had 3, but I'm limited by the 2 measurements that had 2 sig figs. So when I round off my answer, I have 600 milliliters, which I can write by putting a line over that first 0 so that just the 6 and the first 0 are significant, or by putting it in scientific notation. My final example is using that STP again to help us come up with a couple of the quantities associated with that sample. Our sample has 3.25 liters at STP, and we want to find the temperature at which the gas will occupy 4.50 liters at 125 kPa. So because this is the second temperature listed, looking at my combined gas law, I would label this one as my T2. So to get T2 by itself, I would need to bring P1 and V1 over to the denominator, so that T2 would equal P2 times V2 times T1, all divided by P1 and V1. Again, I'm going to go back up to the very beginning of my problem and identify my variables. I have 3.25 liters, that's the first volume I've seen. So the temperature and pressure associated with that would be my T1 and my P1. We're going to come back to that STP in a second because we've been talking about the need for consistent units. And we may be able to decide what units of pressure we need based on our other pressure in the problem. Remember, temperature has to be in Kelvin, so we'll always want to convert that 0 degrees Celsius to Kelvin. We know what we're looking for, T2, so the pressure and volume associated with T2 are also going to be in 2's. So the 4.50 liters, which is what the gas would be at, that temperature would be my V2, and then the 125 kPa, its pressure, would be my P2. Again, going back to STP, I see that my P2 is in kPas, so when I look at STP, I'm going to want to use the pressure that 1 atmosphere is equivalent to in kPas, which is 101.325. Remember that from your pressure conversions in the first video you watched. Because temperatures need to be in Kelvin, I went ahead and turned 0 degrees Celsius into Kelvin by adding 273. And so I should be ready to go with using this equation. My P2 will be the 125 kPa, my V2 will be the 4.50 liters, and my T1 is the STP temperature in Kelvin, 273. I'm going to divide by P1, which will be my STP pressure in kPa, so that it'll cancel with my P2. And then V1 was what I was given at the very beginning of the problem, 3.25 liters. I should be okay with units. It looks like the volumes are consistent, as are the pressures. That leaves me with a Kelvin unit for temperature, and that is again the only unit that I can come out of a gas law equation with for temperature. I have to solve for it in Kelvin, even though I'm starting with Celsius, or I could have started with Celsius, and I'm going to Celsius. Multiply across and divide. The measurements, the volumes that were given, as well as the pressure that was given, are all in 3 sig figs. STP is a defined value, so we don't worry about that for sig figs. And that gives me a temperature, when I put it in the calculator correctly, of 466 Kelvin. The question asks us to find the temperature in Celsius, and since it specified that, we will need to do one final conversion, subtracting 273 away from that Kelvin temperature to get it to Celsius. And when we do that, because the Kelvin temperature went to the ones place, we also want to report our Celsius temperature to the ones place, and we'll get 193 degrees Celsius. This is the end of part 4. You should be able to do the combined gas law worksheet and combined gas law worksheet 2 at this point.